friends, welcome to my channel. So in the today's lecture, we are going to discuss one another CPU scheduling algorithm, shortest remaining time first. Okay, shortest remaining time first. It is a preemptive algorithm. Okay, like we discussed in the last video, round robin algorithm. It is also preemptive algorithm like round robin. Okay, if you have watched my last video of round robin, in that algorithm, what we were doing, we were allocating our one CPU to many processes for equal amount of time. Okay, we were allocating one CPU to many processes for equal amount of time. Okay, let's suppose I have three processes, process 1, process 2 and I have process 3. Okay, and I am having one CPU. So what I was doing in round robin algorithm, I was giving this one CPU to many processes for equal amount of time. Like firstly, I give this process 1 CPU for 3 units of time. Okay, then I switched my CPU to process 2. I give this process to CPU for 3 units of time. Okay, so we were sharing our CPU among many processes for equal amount of time in round robin algorithm. But we really have a disadvantage of round robin algorithm. Okay, what we want to do, we want to reduce the response time. We want to execute many number of processes as fast as possible. We want to reduce the waiting time of the processes. But let's suppose if your time quantum is very large, like 10 units. Okay, if your time quantum in round robin algorithm is very large, it is around 10 units. Okay, so what does it mean? That to each and every process you will be allocating CPU for 10 units of time. Okay, so your process has to wait for 10 units of time to get the CPU. Okay, if you have allocated your CPU to process 1 for 10 units of time, you cannot give CPU to process 2 before 10 units. Okay, so your process 2 has to wait for 10 units of time. So obviously, as our time quantum is going to be increased, your response time is going to be increased. Okay, your response time is going to be increased. But we have to reduce our response time. We want to execute many number of processes as fast as possible. So by looking at this problem of round robin algorithm, we thought of shortest remaining time first algorithm. Okay, and this shortest remaining time first algorithm is a preemptive version of shortest job first. Okay, I have made one video on shortest job first. Your shortest job first algorithm is a non-preemptive algorithm, and it is a preemptive version of shortest job first. By looking at this problem of round robin, we tried to improve the performance of our algorithm. We are giving more priorities to the shortest jobs. Okay, because if you start executing your shortest shortest job in the starting. Okay, if you start executing your shortest job in the starting, then in a very less time you will be executing many number of processes. Okay, so waiting time of the processes is going to be reduced. Your starvation problem is going to be reduced in shortest remaining time first. Okay, so now let me check the performance of this algorithm. Let's take one example. Let's suppose we have a process ID, we have arrival time, okay, we have a CPU time or burst time. Okay, we have four processes P1, P2, P3 and P4. Okay, and their arrival times are 1, 2, 3, 4. Okay, and the burst time is 5, 4, 2, 3. Okay, let's apply shortest remaining time first algorithm on this input. Okay, this is the input. Let's check how well this algorithm is going to perform. Okay, let me make Gantt chart for it. Okay, so I am starting here from 1. So in the starting, which processes we have in the main memory in the starting? In the starting, we have only one process present in the main memory. Okay, its arrival time is 1. So now you don't need to think anything. Okay, you just have one process in the main memory. You just give this process 1 to CPU. Okay, so we are giving this process to CPU. And it is a preemptive algorithm. Okay, I will tell you how this algorithm is going to work. How we are going to switch your CPU between processes. Okay, so I allocated CPU to this process 1. Okay, now I executed this process on CPU for just 1 unit of time. Okay, now I see that when I executed my process P1 for 1 unit of time, at 2 there is one more process coming in the main memory. Okay, so now there is one more process present in the main memory. So I will check its burst time. I will check if the process which is present in the main memory has less burst time than the currently executing process. Okay, now your process P1 is executing, but I will try to check. I will always keep my eyes in the main memory. So you will be checking at each and every point of time that how many processes are coming in the main memory and what is their burst time. You will compare the burst time of the processes present in the main memory with the currently executing process. Okay, if the process which is present in the main memory has less burst time, has less CPU time than the currently executing process, then you will preempt your process. You will be giving your CPU to the shortest process. Okay, we will take back CPU from the currently executing process and we will assign that CPU to the shortest process. Okay, so I executed process P1 for 1 unit of time, and at 2 I see that process P2 is present in the main memory. Okay, and I will check the burst time of this process P2. Its burst time is 4. Okay, so if you look at your currently executing process and the process which is present in the main memory, both worry. Okay, both has the same burst time. So you will continue executing your current process. Okay, you will keep on executing your process 1. So I am executing my process P1 for 1 more unit of time, 3. Okay, so if you look at point 3, we have one more process present in the main memory. Okay, now we have 2 processes present in the main memory, P2 and P3. And I will check their burst time. Its burst time is 4. Okay, which is, now it need only 3 units of CPU time. Your process P1 now need only 3 units of CPU time. It has been executed on CPU for 2 units of time. Okay. So if you look at your process P2, its burst size is bigger. Its burst time is bigger than the burst time of process 1. Okay, so we will not execute this process P2 because we need shortest job first. Okay, now we have one more process present in the main memory P3 and its burst time is 2. Okay, if you look at, this is my currently executing process P1 and its burst time is 3 and this process P3 burst time is 2. It has less burst time than process P1. So I will be taking back CPU from process P1 and we will give CPU to process P3. Okay, so now I am giving my CPU to process P3. Okay, and now I am executing it for 1 point of time. Okay, now it's only 1 unit is left. Okay, and now if you look at P4, now your process P4 is also present in the main memory. Okay, so if you check the burst time of process P4, its burst time is actually 3. Your process P4 burst time is actually 3. Okay, which is larger than your currently executing process. Okay, so you will continue executing your process P3 because we always give priorities to the shortest jobs first. Okay, we always give priority to the shortest job. So you will be executing your process P3. Okay, it needed only 1 unit of time. We will be giving CPU to this process for 1 unit of time. Okay, so now it has been completely executed. It has been now completely executed. Okay, now we have these 3 processes P1, P2 and P4 present in the main memory. Okay, now we will give chance to the process having shortest burst time. Okay, if you look at this process P1 and P4, both have the 3 burst time. Okay, both need 3 units of time of CPU. So if there is any clash, if you find the same values, then we give priority to the first come first serve. If there is any tie, we will be resolving it with first come and first serve. Okay, so I will be executing my process P1 firstly. Okay, 3, 4 and 3. So I will be executing this process P1 on CPU for 3 units of time. Okay, because 3, 4 and 3, we have these 3 processes. Okay, so I will be executing my process P1 for 3 units of time, 8. Okay, so now your process P1 is over. Your process P1 is over, your process P3 is over. Now we have P2 and P4 present in the main memory. Okay, I will be giving chance to the process having shortest job, having shortest burst time. Okay, so I will be allocating CPU to process P4. Okay, I I will be executing this process on CPU for 3 units of time. So 8 plus 3, 11. Okay. Next we have only process P2 pending in the main memory. I will be giving CPU to this process P2. Okay. So P2, it want to execute on CPU for 4 units of time. So 11 plus 4, 15. Okay. So this is actually our Gantt chart. This is how shortest remaining time first works. Okay. In the middle of the execution of the process, you can stop executing your process. You can pause your process. Okay. You can pause your execution of process. At any point of time, you can switch your CPU to another process. Okay. So now let's try to calculate the completion time, the turnaround time, the waiting time and the response time. Okay. So now let's try to find out the completion time of all of the processes. Your process P1 arrived at 1. Okay. And it got completed at 8. Okay. It was given CPU 2 times. Once it was given CPU at the starting, and then we found one new shortest process in the main memory. So we switch our CPU to that process. Okay. And this process P1 had to wait for some amount of time. Okay. So it is actually getting terminated at 8. So what is the completion time? 8. Next process P2. Process P2 is getting completed at 15. Okay. Your process P2 is getting completed at 15. As its burst time is larger than these processes. Okay. So it had to wait for some amount of time to get the CPU. It is getting completed at 15. Next we have process P3. Process P3 completion time is 4. Its burst time is the smallest of all the processes. So as it is coming in the main memory, it is given CPU on the spot. Okay. And it gets executed. Okay. It arrived at 3. It was executed on CPU at the same time. So it gets completed at 5. It needed 2 times burst time. Okay. So 3 plus 2, 5. Okay. It arrived at 3. It executed on CPU for 2 units of time. So 3 plus 2, 5. So your process P4 arrived at 4. Okay. And it had to wait for some amount of time. Okay. It gets completed at 11 units of time. Okay. So now let's see what is the turnaround time. What is the turnaround time? So turnaround time is completion time minus arrival time. How long your process has been alive in this cycle? Okay. How many times your process gets executed on CPU? Plus how long your process was waiting for the CPU. Okay. If your process wants a CPU, it doesn't mean that you will be giving CPU to that process when that process requests for CPU. No. You will allocate CPU to the process on the basis of your type of algorithm. What algorithm you are using. Okay. It is not that if some process requests for CPU, we are giving to the CPU. There is a chance that process might have to wait for some amount of time to get the CPU. So, what is the completion time? So, this process arrived at 1 and it gets completed at 8. So, how long it has been alive in the cycle? 8 minus 1, 7. once it entered in the main memory and once it is getting out of the main memory. Okay, once it is getting in the main memory and once it is terminated, the intermediate time, we will be calling it as a turnaround time. Like if you are opening MS Excel, you double click on MS Excel file and whatever work you wanted to do, you have done all of that work and now you are closing your application. You are terminating your application. So how long you have worked on your application? How long your application was opened? That is a complete cycle. Okay. So that is actually our turnaround time. And what is the turnaround time of process P2? Completion time minus arrival time. It remains alive in the cycle for 30 units of time. Let's try to find out the turnaround time of your process P3. Okay. So completion time minus arrival time. 5 minus 3, 2. Okay. It was alive in the cycle only for 2 units of time. Your process P4 arrived in the main memory at 4 and it gets terminated at 11. Okay. So how long it has been alive in the cycle? For 7 units of time. Either it is waiting for CPU or either it is running on CPU. Okay. So this is the turnaround time. How we will be calculating the waiting time? Turnaround time minus burst time. Okay. The total time in which your process was alive minus the execution time. How much time your process was executing on CPU. So the remaining time your process was waiting for the CPU. Okay. That is actually the waiting time. So your process P1 arrived in the main memory at 1. Okay. And how long it had to wait for the CPU? Initially, it was given CPU 2 times. Okay. The first time it was given CPU at 1 when it arrived. Okay. But we executed this process for some units. Then we found some another shortest process in the main memory. So we switch our CPU to that shortest process. Okay. So then this process had to wait for some amount of time to get the CPU. So after 3 it was given CPU again at 5. Okay. So how long it had waited for CPU? From 3 to 5. 2 units of time. Okay. Or you can calculate it this way. Turnaround time minus burst time. The remaining time is the waiting time. Turnaround time minus burst time. Okay. 7 minus 5, 2. This is actually the waiting time. Your process P2. It arrived in the main memory at 2. Okay. But it was allocated CPU at 11. So how long it waited to get the CPU? It waited for 9 units of time. Okay. It waited for 9 units of time. You subtract 13 minus 4, you will get 9. Next we have process P3. Process P3 arrived in the main memory at 3. And it was allocated CPU at the same time when it arrived because its burst time is very less than all the processes. Okay, so it was given more priority among other processes. Okay, so what is the waiting time of this process P3? Its waiting time is 0. Okay, it didn't wait any point of time. As it is coming in the main memory, you are giving CPU to it. So waiting time is 0. Turnaround time minus burst time 2 minus 2, 0. Next we have process P4. So it arrived in the main memory at 4 but it was given CPU CPU at 8. Okay, it was given CPU at 8. It had to wait for 4 units of time to get executed on CPU. Okay, 7 minus 3, 4. So this is actually our waiting time. Now let's calculate the response time. If you look at your process P1, it is arriving in the main memory at 1. Okay, after its arrival in the main memory, how long it is waiting to get the first time response from the CPU? Okay, it is arriving in the main memory at 1 and it is given CPU on the spot. So it didn't wait any time. So 1 minus 1, 0. Okay, your process P2, it is arriving in the main memory at 2 and it was given CPU at 11. It was given CPU at 11. It was given first time response from the CPU at 11. So how long it had to wait to get the first response from CPU? 11 minus 2, 9. Okay. Next we have process P3. It arrived in the main memory at 3 and it was given first time response from the CPU at 3. Okay. As it is the shortest process than all of the other processes, we are giving it priority. As it is coming in the main memory, we are scheduling it. Okay, we are giving it to CPU. So it didn't wait any point of time. 3 minus 3, 0. Next we have process P4. It is arriving in the main memory at 4 and when it was given first time response from CPU at 8. Okay, it was given CPU at 8. It had to wait for 4 units of time after it is coming in the main memory. So 8 minus 4, 4. Okay, so this way we are going to calculate the shortest remaining time first. We always try to give priority to the shortest processes so that we can reduce the waiting time and the response time. Okay, so whatever we are discussing it for a single machine. Okay, how I am discussing that if you are using a single machine and you are opening many files or many number of processes in your machine, in your computer. Okay, how to perform multitasking in a single user system. Okay, if you are a single user and you are performing multitasking, you are doing lots of tasks in your machine. Okay, but these algorithms are really going to be helpful even if we have a client server architecture. Okay, we have a one server and in the today's world we are using internet. At a one particular point of time, lot of people connect to the network at the same time. So we all are requesting to the server for the web pages. Okay, we are doing many number of requests to a one machine, to a one server. If you are doing the client server architecture, even if you talk about the networking, at a one particular point of time, many number of people are getting connected to the same machine. They are requesting for web pages to the server. Okay, so your server has to process lots of requests. Your one machine is getting lots of requests. So your machine, your server has to respond to all of that requests. How it is going to process many number of requests? With the help of which algorithm? It is going to process multiple requests so that we can reduce the waiting time of the users. We can provide service to many users as fast as possible. Okay, so we also need to take care of it. Okay, so our purpose is we want to reduce the waiting time and the response time. We want to process all of the requests as fast as possible. We want to improve the speed. We want to improve the performance. So that is our main motive of studying all of these different algorithms. Okay, if you are finding some drawback of one algorithm, then we are trying to improve that drawback in the next algorithm. Okay, so I hope that you are clear with this algorithm. If you have any query, I have mentioned my email ID in the description box. You can contact me on that email ID. If you like my video, please like, share and subscribe my channel.